On a winter evening in Berlin, a physicist sat with a problem that seemed far too small to threaten the great architecture of science. The question was simple enough to state: when matter is heated until it glows, how exactly is that light distributed? It was the sort of problem that belonged to laboratories, furnaces, and careful measurements, not the sort of problem that should disturb the deepest assumptions of physics. And yet, as the numbers grew more precise, something unsettling began to appear. The equations that had once carried such confidence into the motions of planets, the flow of heat, and the behavior of waves were beginning to say something absurd. This was the strange position of physics at the end of the 19th century. It was powerful, elegant, and in many ways astonishingly complete. Nature seemed, at last, to be yielding its structure to human thought. There were still details to refine, still difficult corners to illuminate, but the foundations appeared secure. The world, so it seemed, was continuous, lawful, and ultimately intelligible in a familiar way. Light spread through space. Energy changed smoothly. Causes produced effects with the steady dignity of a universe that could be pictured, measured, and understood. But hidden inside that confidence was a weakness. The closer physicists came to one universal law of thermal radiation, the more clearly they saw that the old picture could not hold. A theory that looked graceful from a distance began to break apart under the pressure of one stubborn fact. And what made the crisis so powerful was not only that the mathematics failed in one narrow place, it was that the repair, when it came, did not feel like a triumph. It felt like a concession, a reluctant opening, a move so strange that even the man who made it did not fully want to believe what it might mean. Tonight, we follow that opening. We begin in a world that still trusted continuity. And we move toward a moment when continuity itself began to look uncertain. We will watch as a technical puzzle about heat and light widens into a deeper unrest about matter, radiation, and the very language of physical reality. How did one quiet mismatch between theory and experiment grow into a crisis that modern physics could not avoid? And what happens when the universe refuses to behave in the smooth, continuous way the human mind had learned to expect? In the closing years of the 19th century, physics did not look like a discipline in crisis. It looked like one of the great intellectual victories of the modern world. Heat had been given laws. Electricity and magnetism had been drawn together into a single field theory. Light itself had been folded into that same electromagnetic picture. Again and again, phenomena that once seemed separate had been shown to belong to a deeper order. The universe, at least in its broad outlines, seemed to be yielding not in fragments but in systems. This mattered not only because the results were impressive, but because they appeared to point in the same direction. Nature looked lawful, continuous, and coherent, a place where causes flowed into effects without sudden ruptures, and where mathematics could move with an almost serene confidence from principle to prediction. That confidence was not merely philosophical mood. It had been earned through a century of astonishing success. Thermodynamics had clarified the relation between heat, work, and energy, turning what once seemed like the vague behavior of fire and steam into something measurable and exact. Electromagnetic theory had gone even further. In Maxwell's hands, electricity, magnetism, and light had ceased to be separate subjects and become different expressions of one structure. When later experimenters confirmed the existence of radio waves and other electromagnetic effects, The theory did not merely survive, it expanded. And when J. Thomson identified the electron in 1897, even the supposedly indivisible atom began to look accessible to physical inquiry. The old world was not closing itself off. It was opening. To live intellectually in such a moment was to feel that science had entered a mature age. Not that every detail was known, and certainly not that every problem had been solved, but that the foundations were sound enough for the remaining difficulties to seem local. There were still stubborn questions at the edges, still experimental puzzles, still mismatches between formula and fact. Yet these were often treated as irregularities within an otherwise stable order. The kind of things that better technique, sharper measurement, or more refined mathematics would eventually smooth away. The image of nature that classical physics offered was not only powerful, it was comforting. Motion could be pictured. Fields could be represented. Energy could be treated as something that changed by degrees, not by leaps. The universe might be subtle, but it did not yet seem hostile to intuition. And yet it is often in just such moments, when a field feels safest, that its hidden weakness becomes hardest to notice. A science can become most vulnerable when its language has become so successful that no one feels much need to question its deepest assumptions. The danger is not stupidity. It is fluency. When a framework explains enough, its basic habits of thought begin to disappear from view. They no longer look like assumptions. They look like reality itself. Late 19th century physics had reached that kind of fluency. It had grown used to the idea that nature would ultimately remain continuous, that processes would unfold smoothly, and that if theory and measurement briefly disagreed, the fault would most likely lie in some temporary incompleteness rather than in the foundations themselves. The first real pressure did not come from the grandest questions. It came from heated matter, a bar of iron in a forge, a filament glowing in a lamp, the shifting colors of a body as its temperature rises from dull red toward white. These were familiar things long before they became theoretical battlegrounds. But by the end of the 19th century, physicists were no longer content merely to note that hot objects glowed. They wanted a precise law describing how much radiation was emitted at each wavelength for a given temperature. The problem belonged partly to pure theory and partly to the practical world of measurement, furnaces, instrumentation, and the growing need to determine high temperatures by radiation rather than by touch or direct contact. It was an old experience turning into a modern question. What made the subject especially powerful was the idea of the black body. A black body was not simply any dark object. In physics, it meant an ideal absorber, a body that took in all incident radiation and, once in thermal equilibrium, re-emitted energy in a universal way determined by temperature alone. In practice, one of the best approximations was a cavity with a small hole, because radiation entering the hole would be trapped and absorbed inside. This turned the problem into something unusually clean. Instead of asking how brass differs from coal, or ceramic from iron, physicists could ask a deeper question. What is the universal spectrum of thermal radiation itself, when the distracting particulars of material have been stripped away as far as possible? That universality gave the problem a special dignity. It was not about one substance. It was about nature under ideal conditions. This is why black-body radiation mattered so much more than its laboratory apparatus might suggest. A universal law is always tempting in physics, because it seems to promise a place where theory can confront the world without excuses. If the emitted spectrum depends only on temperature and not on the specific identity of the material, then any successful explanation begins to look foundational. The black body became a stage on which nature might reveal not merely a practical regularity, but something very close to first principles. There was elegance in that ambition. A heated cavity, a narrow opening, a careful set of measurements, and from these humble arrangements, the possibility of touching the architecture of reality itself. Wilhelm Wien brought the problem to a remarkable level of precision. His work on thermal radiation captured important features of the spectrum and gave physicists a law that worked impressively well in part of the observed range. That near success is crucial to the story. The radiation problem did not first appear as chaos. It appeared as closeness. A pattern was clearly there. The data were not random. The universe was not behaving wildly. In fact, it was behaving in a way that seemed almost ready to submit. And that made the remaining mismatch more, not less, frustrating. The nearer a theory comes to the mark, the less willing one becomes to imagine that the entire conceptual background might be wrong. Wien's success, therefore, had a double effect. It advanced the field, and it encouraged the belief that a complete classical account must be nearby. Among those drawn deeply into this question was Max Planck. Looking back later, he said that for many years he had aimed at solving the problem of the distribution of energy in the normal spectrum of radiating heat. That recollection tells us something important. This was not a fleeting curiosity, nor a passing technical nuisance. It was a long-standing challenge that had taken hold of a serious theoretical mind. Planck was not approaching the subject as someone eager to overthrow the old order. Quite the opposite. He was a man formed within that order, trained to respect general principles and to seek exact laws. The attraction of the blackbody problem for someone like him lay precisely in its apparent purity. Here was a phenomenon so universal, so sharply defined, that if one could derive its law cleanly, one might strengthen rather than weaken the classical picture. There was another reason the problem felt safe enough to pursue without fear. Classical physics already had ways of imagining what radiation inside a cavity ought to be like. One could think in terms of standing electromagnetic waves and resonant modes, each contributing to the energy present. One could imagine heat distributing itself among available degrees of freedom in a way continuous theories found natural. None of this initially sounded reckless. It sounded exactly like the sort of reasoning that had worked elsewhere. When a theoretical culture has solved so much, it does not easily suspect that its best habits might become its trap. The radiation problem looked, at first, like an invitation to extend classical thought, not to abandon it. And this is what gives the opening of the quantum story its peculiar emotional texture. We often tell revolutions in retrospect, as if their protagonists sensed from the beginning that they were standing at a cliff edge. Most of the time, they do not. They believe they are tidying up, refining, completing. The language of late classical physics was still strong enough that anomalies were interpreted as unfinished business within a largely secure framework. Even the atmosphere of measurement encouraged that belief. Better instruments often resolved old tensions. More exact data often clarified hidden regularities. Why should this case be different? Why should one radiation law, however delicate, be the place where the continuity of nature itself would begin to look suspect? At that stage, there was little reason to think so. Yet the danger was already present in the very qualities that made the problem attractive. Because blackbody radiation was so universal, any persistent failure here could not be shrugged off as a quirk of copper or soot or glass. Because the measurements were becoming so precise, the gap between expectation and observation could not forever be hidden inside experimental uncertainty. And because the classical account was so elegant, every serious mismatch threatened to expose not a missing detail, but a structural weakness. The old worldview had become strong enough that only a narrow, exquisitely clean problem could really wound it. A Messier phenomenon might have been dismissed or postponed. This one could not. So the stage was set in a quiet way, not with public drama, not with philosophical manifestos, but with furnaces, cavities, wavelengths, and the growing insistence that thermal radiation obey a law no one had yet fully secured. Physics still believed in itself. It still had excellent reasons to believe in itself. Theoretical unification, experimental success, and expanding control over matter and measurement had made that confidence seem not only natural, but deserved. And precisely because it was deserved, what came next would strike with unusual force. A weak science can survive anomalies by blaming its immaturity. A mature science is forced to take them personally, section by section. This story will move toward the moment when continuity begins to fail. But at the start, that failure is not yet visible in full. What we have instead is a civilization of thought near the height of its composure, turning its attention to a stubborn and seemingly manageable problem in radiant heat. The world still appears smooth. Energy still seems the sort of thing that should vary without interruption. Nature still looks from a distance, as though it will remain picturable in the old way. That is why the next step matters so much. Before the crisis could become philosophical, it had to become physical. Before it could shake the meaning of light, it had to take shape inside the furnace. If the first crack in classical confidence was going to appear anywhere, it was fitting that it should appear in something so ordinary that people had watched it for centuries without suspecting what it concealed. A body is heated. At first it remains dark. Then it begins to glow with a deep red. With more heat, the glow brightens, shifts, sharpens, moving toward orange, then toward white. This familiar progression belonged to blacksmiths, glass workers, metal workers, and instrument makers long before it belonged to modern theory. It was part of the visual education of human beings. Fire changed matter, and matter answered with light. What physics did in the 19th century was not discover that fact, but begin asking it a new kind of question. Not simply why hot things shine, but how much they shine at each wavelength, and whether that distribution follows a universal law. That shift, from noticing the glow to demanding its exact structure, changed everything. Once measurement becomes precise enough, familiar phenomena stop being merely familiar. They become tests. The glow of heated matter could no longer remain a poetic sign of temperature or a practical sign of work done in a furnace. It became a spectrum. It became a curve. It became a place where nature either agreed with theory or refused to. And because the problem sat at the intersection of heat, light, and equilibrium, it drew together some of the strongest domains of classical physics at once. If thermodynamics and electromagnetic theory both described nature so successfully, then surely the radiation of a heated body ought to fall gracefully into place within that order. The question did not initially feel revolutionary. It felt like the sort of problem a mature science should be able to complete. Part of what made the problem so compelling was that it had already been purified by earlier thought. In the middle of the 19th century, Gustav Kirchhoff helped transform the study of thermal radiation by arguing that under thermal equilibrium, there exists a universal relation between emission and absorption, and that the radiation inside a cavity should in principle, have a form independent of the particular material making up the walls. Planck later recalled the significance of this step very clearly. Since Kirchhoff had shown that the state of heat radiation in a cavity bounded by emitting and absorbing substances of uniform temperature must be independent of the nature of the bodies, the question became unusually exact. One was no longer trapped in the endless particularities of brass, porcelain, soot, or polished metal. One could ask instead for the law of the radiation itself. The blackbody emerged from that ambition. In the abstract language of physics, it meant a perfect absorber, an ideal body that takes in all incident radiation. But what gave the idea practical power was the cavity. A small opening in an enclosed heated cavity could behave as an excellent approximation to a blackbody, because radiation entering the hole would bounce, scatter, and effectively be absorbed within the interior. The light leaving that opening would then represent not the caprice of a particular substance's surface finish, but the more universal radiation field established within the cavity at a given temperature. Even in modern metrology, blackbody cavities remain central precisely because this geometry creates extremely high effective emissivity. The elegance of the setup lies in how little it seems to promise. A hollow space, a narrow aperture, a temperature held steady. And yet from this austere arrangement, physicists hope to extract a law that belonged to nature at its most impersonal. There was something almost moral in the attraction of such a problem. Physicists have always loved places where excuses disappear. A universal law of radiation would be such a place. If the spectrum depends only on temperature, then theory can no longer retreat into special pleading. It cannot say the anomaly belongs only to iron, or only to carbon, or only to some peculiar surface chemistry. The blackbody promised a confrontation between mind and world in one of its cleanest forms. That is why the subject drew such concentrated attention. The problem of thermal radiation was not just another branch of heat. It was an ideal testing ground for the entire classical habit of explanation. And the problem was not merely theoretical. It was fed by the practical demands of measurement and illumination. Wilhelm Wien's noble biography notes that his work on heat radiation grew out of an institute concerned with practical and technical questions, including the measurement of high temperatures and the behavior of radiant energy. In that sense, the blackbody problem belonged both to abstraction and to craft. It lived in laboratories, but it also touched industry, lamp technology, and the broader effort to make heat visible and measurable with increasing precision. This is important because it kept the crisis grounded. The coming rupture in physics did not begin with philosophers arguing over first principles in empty rooms. It began with disciplined attempts to understand radiation well enough to measure, compare, and use it. Wilhelm Wien became one of the central figures in this tightening drama. In the 1890s, he pursued the blackbody problem with great skill, extending thermodynamic thinking into the domain of radiation and defining the ideal black body in a form that helped sharpen the whole field. His Nobel biography notes that in 1894, he published work extending concepts such as temperature and entropy to radiation in empty space. And in 1896, he produced the formula that became known as Wien's law, derived in the course of seeking the composition of the radiation of a black body. This was not a minor advance. It gave physicists a real handle on the spectrum. It captured important features of observed radiation and, perhaps even more significantly, suggested that the spectrum structure could indeed be expressed through an elegant mathematical relation. Wien's achievements had a very particular narrative effect on physics. They did not throw the field into confusion. They brought it tantalizingly close to completion. His displacement law showed that as temperature rises, the wavelength at which the radiation is most intense shifts. The hotter the body, the further the maximum moves toward shorter wavelengths. This made immediate physical sense to anyone who had seen heated metal change color from red toward white. But now the shift could be treated in a universal and quantitative way. In his Nobel lecture, Wien connected this understanding not only to laboratory radiation, but even to the solar spectrum, emphasizing how the maximum of radiation and the temperature of a black body could be related in a principled way. That kind of success deepened confidence. It made the overall problem seem difficult. Certainly, but not alien. A path was visible. The spectrum was yielding its regularities. The universe still appeared willing to be described in the old language. And yet, near success can be more dangerous than obvious failure. When a law works impressively well in one part of the observed range, it becomes harder to imagine that the whole framework might be compromised. One begins to think in terms of correction rather than replacement. This is what makes Wien's place in the story so important. He stands not as the man who failed before the real answer arrived, but as one of the men who made the problem sharp enough to become unavoidable. His law was a genuine achievement. It explained enough to show that the radiation spectrum had deep structure, but it did not explain everything. The better the measurements became, the clearer it was that no partial success could be mistaken for the full universal law Kirchhoff's vision had demanded. This was the pressure chamber, not a collapse into chaos, but a slow narrowing of possibilities. On one side stood the prestige of classical reasoning. Radiation in a cavity could be imagined in terms of continuous electromagnetic processes. Energy, in the classical picture, was not the sort of thing that came only in indivisible pieces. It varied smoothly. It spread across possibilities without ontological embarrassment. On the other side stood the increasingly disciplined evidence of the blackbody spectrum, which seemed to demand an exact law and refused to be fully satisfied by elegant approximations alone. The problem did not scream. It insisted. It remained there, in quiet defiance, precisely where classical theory expected to look strongest. There is a special kind of tension that arises when a science cannot yet see whether its obstacle is deep or shallow. If the obstacle is shallow, then all that is needed is technique, a refinement, a better derivation. If it is deep, then the entire grammar of explanation may have to change. In the late 1890s, the blackbody problem hovered in that uncertain zone. It could still be treated as one of the final adjustments to an already triumphant physics, but it had begun to acquire a more disturbing character. The cavity was too clean, the universality too strong, the measurements too persuasive. Each attempt to solve the problem was also, implicitly, a test of whether classical continuity was as natural as physicists had assumed. This is why the furnace problem mattered so much more than its humble apparatus might suggest. A heated cavity is not visually dramatic. There are no planets colliding, no thunderous machines, no vast observatories turning toward the heavens. There is only a controlled interior, a disciplined equilibrium, and the light that leaks from a small opening. But in that light lay a question of unusual severity. Was radiation really something the classical world could distribute continuously and universally without contradiction? Or had physicists mistaken a powerful habit of thought for a law of nature? The beauty of the blackbody problem is that it did not announce the larger question at once. It let the larger question arrive slowly, through the repeated embarrassment of a system too elegant to fail lightly. For the men working on it, the situation would not have felt theatrical. It would have felt demanding, technical, perhaps even tedious at times. That too is part of the truth. The making of a scientific crisis is often much quieter than the retrospective story. Hours of calculation, tables of measurements, small discrepancies, competing forms for a curve. The steady pressure of a problem that refuses to become beautiful in the right way. Yet this quietness is exactly what gives the episode its force. Nothing in the external scale of the problem prepared physics for the scale of its consequences. A discipline that believed it was refining one corner of heat theory was, without quite knowing it, approaching one of the decisive thresholds of modern thought. And so the furnace became more than a source of heat. It became a place of intellectual compression. Inside the blackbody problem, the old faith in continuity was not yet broken, but it was being tested under unusually pure conditions. Wien had brought the field to a point where the structure of the spectrum could no longer be treated loosely. Kirchhoff had already framed the search as one for a universal law. Precision had taken away the comfort of vagueness. Physics had moved too close to the heart of the matter to retreat into imprecision, and yet not close enough to secure peace. This was the atmosphere into which Max Planck stepped with increasing seriousness. He did not enter a chaos of failed thinking. He entered a problem that had become too exact to ignore, too elegant to dismiss, and too narrow, at first glance, to seem capable of changing the foundations of the science itself. From here, the story tightens around one mind. The furnace problem had prepared the ground, stripped the question of unnecessary distractions, and made the stakes more severe than they first appeared. What remained was to find the law, and in searching for that law, Planck would make a move that looked at first like an answer to the spectrum alone, but would turn out to be the opening through which the whole old continuity of physics began to give way. When the blackbody problem narrowed toward Max Planck, it did not yet look like an invitation to revolution. It looked like a demanding but dignified theoretical task. The sort of task a physicist shaped by thermodynamics might reasonably hope to solve without breaking the deeper order of things. Planck's own intellectual formation helps explain why. His earliest work had been in thermodynamics, an area he took up under the influence of Kirchhoff and Clausius, and when radiation problems drew him in. He treated them as continuous with the larger search for lawful relations between energy, temperature, and equilibrium. In the Nobel biographical account, his work on radiation processes led him to the spectrum of full radiation precisely because experiment had begun to diverge from the predictions of classical physics. But that divergence did not yet suggest to him that the foundations themselves should be abandoned. It suggested that a more exact derivation was needed. There is something important in Planck's own later recollection of this period. In his Nobel lecture, he says that he approached the cavity radiation problem with what would now seem almost innocent expectations, believing that the laws of classical electrodynamics, if handled generally enough and without special hypotheses, ought to be sufficient. He imagined Hertzian oscillators inside a reflecting cavity, exchanging energy through electromagnetic waves until the stationary radiation demanded by Kirchhoff's law was established. That image is worth lingering over because it captures the tone of the whole moment. Planck was not standing outside classical physics preparing to overthrow it. He was standing deep inside it, trying to let its own resources reach one of their last unsolved destinations. This is what gives his role such a distinctive emotional quality in the history of modern physics. He is often remembered as the man who opened the quantum age, and that is true. But he did not open it in the manner of someone delighting in the collapse of the old order. The most revealing thing about Planck is that he was trying, for as long as possible, to preserve a lawful continuity between classical principles and the stubborn data of thermal radiation. His lecture makes clear that he first pursued the problem in the language of resonators, fields, and stationary energy exchange, hoping classical electrodynamics would yield the desired radiation law. Even his early detours, including his avoidance of Lorenz's electron theory, because he did not fully trust the electron hypothesis, show a mind searching for the safest route to generality rather than the boldest route to upheaval. Yet the search refused to stay safe. In the Nobel lecture, Planck says plainly that his first attempt went wrong. His initial hope that emitted radiation might be distinguished in some decisive way from absorbed radiation, allowing a differential equation to reveal the stationary spectrum, failed him. That failure matters because it marks the point where classical fluency begins to lose its ease. A strong theoretical tradition can survive one disappointment without much damage. But a particular kind of discomfort begins when the wrong turn is not just a miscalculation, but a sign that the familiar style of derivation is no longer carrying one cleanly toward the phenomenon. The blackbody problem was becoming more than a missing formula. It was becoming a place where the old reasoning no longer knew how to move gracefully. Planck's next move came from thermodynamics rather than from any immediate desire to atomize light. He says in the same lecture that his earlier studies of the second law of heat theory proved useful, and that from the start he tried to connect not temperature directly to the resonator's energy, but entropy to energy. More precisely, the second derivative of entropy with respect to energy. This is one of those moments in scientific history that can seem technical from the outside and yet carry enormous narrative weight. Planck was not trying to imagine little packets of light bouncing through space. He was trying to secure a physically meaningful relation consistent with the deeper architecture of thermodynamics. Even here, his instinct was conservative in the best sense. He was searching for a bridge, not a rupture. That search drove him toward Boltzmann's ideas about entropy and probability. In the lecture, Planck recalls that after some of the most strenuous weeks of his life, the connection between entropy and probability opened a new perspective. He pursued a combinatorial method for calculating the probability of a given energy distribution among resonators, and this led him to exactly the entropy expression required by the radiation law. The importance of this step is easy to blur in hindsight. What later generations remember as the birth of the quantum often began, for Planck, as an effort to give a true physical character to a formula that already worked. He had found the law, but he still wanted to understand why it held. That is a deeply classical impulse. The law alone was not enough. It had to be reconciled with intelligibility. In 1900, he announced the derivation that would become inseparable from his name. The Nobel biographical page states that he deduced the relation between energy and frequency of radiation in a paper published that year, based on the revolutionary idea that the energy emitted by a resonator could take only discrete values or quanta, with the energy of a resonator of frequency V given by HV. The 1918 Nobel presentation speech also frames the moment in similar terms, saying that Planck found the general radiation formula in 1900 and that the product HV represented the smallest amount of heat that could be radiated at a given frequency. Even stripped of later mythology, this was an extraordinary step. A problem that had been expected to yield to continuity was answered by discontinuity. What makes the moment so powerful, though, is that the step did not arrive with fully visible consequences. The Nobel biographical account is explicit that the discovery marked a turning point in the history of physics, but that its far-reaching effect on classical physics was not appreciated at first. This is essential to the emotional truth of the story. Planck's result was not instantly recognized as the beginning of a new worldview. It appeared first as a successful law, a formula that matched the spectrum where earlier attempts had fallen short. The mathematical victory came before the philosophical surrender. That order matters because it explains why the quantum could enter physics not as an announced revolution, but as an answer no one could easily discard. There is, in fact, a quiet asymmetry at the heart of Planck's achievement. On the one hand, the new law solved the furnace problem with a precision that could not be ignored. On the other, the conceptual cost of the solution remained strangely unresolved. Planck himself, in the later lecture, describes the constant h as an elementary quantum of action and says that once it could no longer be treated as negligibly small, a chasm opened up. Either it was a fictional quantity, in which case the whole derivation was essentially an empty play on formulas, or it pointed to something fundamentally new that would revise physical thought built upon the continuity of causal connections since Newton and Leibniz. That is as close as one can come to hearing the ground shift under classical physics in the voice of one of its own most disciplined practitioners. Notice the order in which this recognition unfolds. Planck does not begin by celebrating a break with continuity. He reaches continuity's limit and only then admits the possibility that the limit is real. His lecture is moving precisely because it preserves the strain of that admission. The quantum of action is not presented there as a decorative new constant to be added harmlessly to the old list. It is presented as something that forces a decision. If real, it compels a revision of physical thinking at a level more basic than any one radiation problem. And yet even here, the revision is not complete. Planck can see the chasm, but he cannot yet cross it in full. He knows something unprecedented has entered physics. He does not yet possess the finished language in which that entrance can be made comfortable. This is why it is misleading to imagine Planck in 1900 as already holding the mature quantum worldview. What he had was something more dramatic in a quieter way. He had a law that worked and a principle that disturbed him. His own Nobel lecture, delivered much later, still emphasizes how difficult it was to incorporate the quantum of action into the well-tried classical theory. And he says plainly that those difficulties had increased rather than diminished. Even by then, with Bohr, Einstein, and others already having widened the meaning of the quantum, Planck still spoke as a conscientious systematologist troubled by the gaps left behind. That posture tells us a great deal about the original moment. The quantum entered physics not as a neat replacement system, but as an unresolved success, a result too powerful to deny and too strange to absorb without pain. There is also something deeply human in the way Planck stands at this threshold. He is not a prophet of disorder. He is a guardian of order, forced to admit that the order he trusted cannot be saved without alteration. That is why his opening is so much richer than a simple breakthrough story. The blackbody problem does not reward flamboyance. It rewards patience, exactness, and stubborn loyalty to the phenomenon. Planck follows the phenomenon farther than the old language wants him to go. In that sense, his greatness lies not only in having introduced quanta, but in having remained honest when his own best intellectual habits led him to a conclusion they could not easily contain. The dignity of the episode comes from restraint. He does not dramatize the rupture. He discovers that he can no longer avoid it. And yet even after the law was in hand, the meaning of the discovery remained suspended. The Nobel biographical account notes that evidence for the validity of Planck's idea became overwhelming only gradually, as it accounted for more and more discrepancies between observed phenomena and classical theory. That gradualness is not a detail at the margins. It is the whole atmosphere of the emerging quantum age. Physics did not wake up one morning and decide continuity was dead. Instead, one successful concession in the furnace began radiating outward into other areas, carrying with it a question no longer easy to contain. If energy exchange in one domain required discreteness, what else might no longer be continuous in the old sense? By the end of Planck's opening act, the blackbody problem had been solved. But peace had not been restored. The furnace had yielded its law, yet the law had brought with it a dangerous remainder. Was quantization only a formal device applying to resonators and their exchange with radiation? Or had physics, almost against its will, stumbled upon a deeper feature of reality itself? That question was still waiting, and it would not be Planck who pushed it furthest. The next decisive move would come from someone willing to make the crisis bolder, someone who would take the success of the radiation law and ask whether light itself had become less continuous than classical physics had ever imagined. If Planck had opened a narrow passage through the blackbody problem, Albert Einstein was the one who forced physics to look at where that passage might actually lead. The difference between them was not a difference in intelligence or seriousness, but in where each man was willing to place the conceptual burden. Planck's quantum step had entered through the exchange of energy between resonators and radiation. It solved a problem, but it still allowed some hope that the deeper structure of light itself might remain essentially classical. Einstein's move in 1905 was more dangerous because it took the success of the quantum seriously in a new way. Rather than treating discreteness as a formal device at the edge of thermal theory, he asked whether the radiation field itself might at times behave as though it consisted of distinct packets of energy. In that moment, the crisis ceased to belong only to the furnace. It began to belong to light. The setting of that move matters. Einstein was still working at the patent office in Bern when he produced the group of papers that would later make 1905 seem almost mythic. But myth can flatten what is most interesting in the episode. He was not tossing out paradoxes for their own sake, nor did he arrive as a theatrical destroyer of old certainties. What makes his 1905 work so powerful is that it grows directly out of the very tensions Planck had left unresolved. Noble's archive notes that Einstein drew his conclusion about the particle-like behavior of light through a statistical analysis of Wien's formula for heat radiation, and then saw that this new idea provided a natural explanation of the photoelectric effect, something the wave theory of light could not adequately do. The point is subtle but crucial. Einstein did not leave the radiation problem behind. He read its implications more radically than others were willing to do. The photoelectric effect had a special kind of importance because it touched the world at once experimentally and conceptually. When light falls on a metal surface, electrons can be ejected. By the end of the 19th century, this was already known. Yet the effect refused to sit comfortably inside the expectations of a purely continuous wave theory. Classical reasoning suggested that the energy transferred to electrons ought to depend primarily on the intensity of the incoming light. More intense illumination should mean more energy available, and therefore, one might expect stronger light to produce more energetic emitted electrons, even if the light were of relatively low frequency. But the actual pattern would not cooperate so neatly. For a given metal, there was a threshold frequency below which no electrons were emitted at all, and above that threshold, the energy of the emitted electrons depended on frequency rather than on intensity. Nobel's Einstein page summarizes the contradiction starkly. According to existing theory, intensity should have been critical yet the effect occurred only when the light was above a certain frequency. This was a very different kind of embarrassment from the blackbody curve, though it belonged to the same growing disturbance. In the furnace problem, classical theory had produced the wrong form for a universal distribution. In the photoelectric effect, the difficulty was more intimate. It touched the very manner in which radiation gives energy to matter. If light were only a continuous wave spreading its energy smoothly through space, then one could imagine an electron gradually accumulating enough of that energy to escape. But the observed threshold suggested something more abrupt and more local. A weak but sufficiently high-frequency light could eject electrons, while intense low-frequency light could fail. The old picture was not merely incomplete here. It was intuitively pointing in the wrong direction. Britannica's summary captures the essential asymmetry. The kinetic energy of emitted electrons depends on the frequency of the radiation, not on its intensity. And there is a threshold frequency below which no electrons are emitted. Einstein's answer was disarmingly simple and therefore deeply unsettling. If light comes in quanta, each quantum carrying an energy proportional to its frequency, then the photoelectric effect ceases to look anomalous. One quantum goes to one electron. If the quantum's energy is too small to overcome the work required to free the electron from the metal, then no emission occurs, no matter how many such low-energy quanta arrive. If the quantum's energy is large enough, the electron can be liberated, and whatever energy remains appears as kinetic energy. This is the structure now familiar from textbooks. But in 1905, it was a conceptual escalation of the highest order. Planck had quantized the exchange of energy in a restricted setting. Einstein was asking physicists to imagine that radiation itself behaves, in at least some circumstances, as though it were made of localized energy packets. Nobel's archival essay is explicit that Einstein saw in his new idea a natural explanation of the photoelectric effect, precisely where wave theory had been unable to provide one. The emotional force of Einstein's move lies in how little room it left for comfortable half-belief. If his law were right, then the quantum could no longer be kept safely inside Planck's original corner of radiation theory. It would no longer be enough to say that matter exchanges energy in discrete ways, while light itself remains serenely wave-like in every essential respect. Einstein was making the crisis bolder by shifting the point of pressure from derivation to ontology. What is light? If frequency determines the energy available to an individual electron, and intensity merely alters how many such encounters occur. Nobel's 1921 prize page says that Einstein explained light as consisting of quanta, packets with fixed energies corresponding to certain frequencies, and that a photon must have a certain minimum frequency before it can liberate an electron. Those statements now sound familiar, but at the time they pressed directly against one of the great achievements of 19th century physics, the electromagnetic wave theory of light. It is worth pausing over how audacious this was. Maxwell's theory had not been a weak or provisional accomplishment. It had unified electricity, magnetism, and light with extraordinary power, diffraction, interference, polarization, and the whole graceful structure of wave optics stood behind it. Einstein was not replacing an exhausted theory with a more successful one in some simple way. He was introducing a second descriptive demand into territory that already seemed magnificently occupied. Nobel's archive later phrased the issue in terms of the dual nature of light. But in 1905, that duality was not yet a peaceful synthesis. It was a provocation. To take light seriously as quanta was not to discard wave phenomena. which were too well established to deny. It was to admit that wave description might be insufficient in situations where energy exchange with matter revealed a different face of radiation. That is why Einstein's paper did not solve one problem and restore calm. It widened the unrest. The reaction was correspondingly mixed. Einstein's law of the photoelectric effect was too sharp to ignore. Yet the conceptual step behind it was too radical to be welcomed easily. Nobel's archival account later noted that the Nobel Committee itself was careful. When Einstein was awarded the 1921 Physics Prize, officially awarded in 1922, the recognition was framed as being for his discovery of the law of the photoelectric effect, not as an unambiguous endorsement of a full particle ontology of light. The same essay remarks that the committee avoided committing itself too strongly to the particle concept and spoke more cautiously about emission and absorption processes. Even at the institutional level, one can feel the hesitation. The law was becoming credible. The worldview behind it was still being approached with reserve. That caution was not simply conservatism in a pejorative sense. It reflected the genuine difficulty of the situation. Light was not ceasing to behave like a wave. The phenomena supporting wave theory remained real and indispensable. Einstein's proposal, therefore, did not offer the sort of clean replacement that scientists often prefer, where one framework simply supersedes another because it explains everything better in one coherent language. Instead, it introduced an uncomfortable asymmetry into the heart of physical description. In some experimental settings, wave language remained essential. In others, the evidence increasingly suggested that light had to be treated as though it came in independent quanta. Nobel's archive even notes that in 1909, Einstein repeated his statistical analysis using Planck's more general formula and argued in a seminar at the Prussian Academy for the necessity of considering light as consisting of a number of independent particles. That detail matters because it shows Einstein himself pushing beyond a one-off explanatory trick toward a broader rereading of radiation. In retrospect, it is easy to say that Einstein had simply seen farther. But the historical experience was far more uneven. Physics was being asked to inhabit a contradiction before it knew how to name it properly. The photoelectric effect did not yet force everyone to abandon waves. It forced them to admit that waves alone were no longer enough. This difference is the key to the whole section. Einstein did not destroy Maxwell. He exposed a limit in the reach of classical continuity when energy transfer had to be described at the level of single events. The threshold frequency, the dependence of electron energy on frequency rather than intensity, and the immediate character of the emission once sufficiently energetic light is present, all pointed toward an exchange structure too discrete to fit comfortably within the old image of smoothly shared wave energy. Britannica emphasizes exactly these features and notes that Einstein's assumptions explain them in a unified way. This is why Einstein's intervention was more than an extension of Planck. It changed the emotional and philosophical location of the crisis. Planck had discovered a law whose derivation required quantization. Einstein turned quantization into a way of speaking about radiation itself. In doing so, he made it much harder to preserve the hope that the old continuous picture would remain fundamental everywhere that mattered. He also introduced a new style of boldness into the story. Planck had entered the quantum reluctantly, as though led there by the pressure of the furnace and the demands of thermodynamic consistency. Einstein entered it by treating the pressure as evidence of something larger. The difference is not between caution and recklessness. It is between solving a problem and allowing the solution to reveal a deeper reality. Yet even Einstein's boldness did not bring immediate peace. A good scientific explanation is not always accepted in proportion to its elegance. Sometimes the very clarity of the explanation sharpens the resistance, because it throws the cost of acceptance into brighter light. To accept Einstein's photoelectric law in its strongest sense was to concede that radiation might not be continuous in the classical way after all. It meant that one of the most successful and beautiful domains of 19th century theory now had to coexist with a disturbing new language of quanta. This is why the next phase of the story matters so much. The question was no longer whether Einstein had proposed something ingenious. The question was whether experiment, over time, would force the wider community to accept consequences it still found conceptually alien. There is a special tension in scientific history when confirmation begins arriving faster than conviction. Einstein had made the crisis bolder, but he had not made it comfortable. The photoelectric effect now stood as a kind of challenge problem thrown back at classical theory. Either one found a comparably natural explanation within the old framework, or one allowed the quantum idea to spread outward from the furnace into the nature of light itself. That second possibility was already underway, whether physicists liked it or not. But acceptance would not come cleanly. It would come through years of measurement, hesitation, reinterpretation, and a widening gap between what the evidence suggested and what many minds were ready to believe. And in that uneasy distance between proof and peace, the next act of the quantum story would unfold. If Einstein had made the crisis bolder, he had not made it easier to live with. That is the peculiar tone of the years that followed. The photoelectric effect gave physics a sharp and elegant law. Yet the law did not produce the kind of calm that comes when a field feels itself returning to order. Instead, it created a strange interval in which evidence began to accumulate while conviction lagged behind. Noble's own archival account of the episode makes this tension unmistakable. Einstein's explanation of the photoelectric effect was recognized as natural and powerful, while the broader particle nature of light remained something the Nobel Committee itself was reluctant to endorse explicitly, even when later prizes were awarded. The theory was beginning to win in practice before it had fully won in the imagination. No figure captures this mood better than Robert Millikan. He was not one of the early champions of the light quantum. In his Nobel lecture, looking back on his experimental work, he recalled that his study of the photoelectric effect had led, contrary to my own expectation, to the first direct experimental proof of the exact validity of Einstein's equation within narrow limits of error, along with the first direct photoelectric determination of Planck's constant. The force of that admission is hard to overstate. It means one of the key experimental confirmations of Einstein's law was produced by a man who had not set out hoping to establish it. The evidence did not arrive wrapped in philosophical agreement. It arrived through disciplined measurement that carried even a skeptical investigator farther than he had intended to go. This is one of the most revealing moments in the whole early quantum story, because it shows that science does not always move forward when its practitioners become inwardly comfortable. Sometimes it moves because the apparatus becomes too honest. Millikan's lecture stresses the precision of what he found. He speaks of confirming Einstein's equation within narrow experimental limits and of obtaining an accuracy of about 0.5%, the best available at the time. Such language belongs to the world of exacting laboratory work, not to speculative metaphysics. And yet the consequence was metaphysical all the same. A law that many found conceptually strange was becoming harder to dismiss, not because the community had collectively embraced a new ontology, but because the measurements had begun closing off the older evasions. What makes this phase historically beautiful in such a quiet way is that the conflict is no longer between theory and observation alone. It is now inside the scientific mind itself. A physicist can confirm a law and still hesitate before the worldview that seems to follow from it. Millikan's own work became one of the strongest pieces of support for Einstein's photoelectric law, and yet the broader meaning of light quanta remained contested. Nobel's archival essay describes this with unusual clarity. The wave theory of light had been quite unable to explain the photoelectric effect naturally. Yet the committee later recognized Einstein carefully, stressing the law of the effect rather than openly affirming a full particle concept of light. In other words, even as the evidence strengthened, the language of official acceptance remained cautious. That caution matters because it tells us something fundamental about the emotional tempo of modern physics. We often imagine discovery as a clean sequence. First comes the bold idea, then the proof, then the consensus. But the actual history is slower and more human. Einstein was awarded the 1921 Nobel Prize, officially presented in 1922, for his services to theoretical physics, and especially for his discovery of the law of the photoelectric effect. The wording is precise. It honors the law, not a triumphant declaration that light has finally been redefined as a stream of particles. Nobel's archival discussion says plainly that the committee did not recognize the particle nature of light when awarding Einstein, just as it later avoided doing so when honoring Compton. Institutions, like individuals, sometimes accept the consequences of a theory more slowly than they accept its usefulness. This was not mere timidity. It reflected a genuine intellectual problem. The wave theory of light had not collapsed. Interference and diffraction had not ceased to exist. Maxwell's theory remained one of the great achievements of 19th century physics, and no one could seriously wish it away. What the photoelectric effect had done was not abolish waves, but expose a region where wave language alone seemed unable to account for what happened when radiation met matter. That is why the committee's caution, awkward though it may seem in retrospect, was historically honest in its own way. Physics was being forced into a double life. In one class of phenomena, light remained unmistakably wave-like. In another, the evidence increasingly pressed toward quanta. The trouble was not that one picture was simply false. The trouble was that no single old picture any longer felt sufficient. No one embodied that strained middle ground more beautifully than Niels Bohr. Nobel's archival account notes that the committee regarded the most important application, and also the most convincing confirmation, of Einstein's photoelectric law as Bohr's use of it in atomic theory. In Bohr's model, the frequency of light emitted or absorbed in a transition between two atomic energy levels obeyed Einstein's relation in a form that modern readers recognize as ordinary energy conservation with a photon involved. Yet the same archival source adds that Bohr resisted the concept of photons for many years, until about 1925. In his 1922 Nobel lecture, he stated with striking frankness that, despite its heuristic value, the light quantum hypothesis was not able to throw light on the nature of radiation because it remained irreconcilable with interference phenomena. It is difficult to imagine a better expression of proof without peace than that. Bohr's position is important not because it shows confusion, but because it shows how profound the conflict had become. He was not rejecting Einstein's law in any simple sense. He was using it. He was building atomic theory partly through it. And yet he was unwilling to say that the photon concept had truly revealed the nature of radiation. This is exactly the sort of tension that makes the early quantum era so unlike the simplified stories told later. A physicist could rely on a formula where it worked, integrated into one of the most successful new models of the atom, and still refused to grant that the underlying picture had become intelligible. The new physics was not being born in a mood of philosophical serenity. It was being assembled through controlled acts of partial acceptance. Seen from that angle, Millikan and Bohr are not opposites, but companions in the same deeper drama. Millikan provided one of the strongest experimental confirmations of Einstein's equation, while not beginning as a believer in its larger meaning. Bohr used Einstein's relation in the heart of atomic theory while resisting the photon as a final description of light. Both men show that the history of acceptance is not the same as the history of discovery. The quantum did not advance simply because everyone immediately saw what it meant. It advanced because it kept working in places where the old order was no longer able to work gracefully on its own. The result was a peculiar intellectual climate, half resistant and half dependent, where each new success of the quantum idea made it harder to contain as a local exception. The pressure increased again with Arthur Compton. Nobel's material on his work explains the result in straightforward terms. According to Einstein's photoelectric effect theory, light consists of quanta with definite energies corresponding to certain frequencies. When Compton directed X-ray photons onto a metal surface in 1922, electrons were liberated, and the wavelength of the scattered X-rays increased because some of the photon's energy was transferred to the electrons. In another Nobel source, this episode is described even more sharply. It was not until 1923, when Compton experimentally showed that a light quantum could deflect an electron just like a corpuscular body, that the debate was over. Whether one takes that phrasing as a clean endpoint or as a dramatic simplification, the direction is unmistakable. Photon behavior was becoming harder to treat as a merely useful fiction. And yet even here, the deeper unrest did not vanish. Compton's result did not return physics to a simple world. It made the strange world more undeniable. If X-rays could behave in scattering events as though they were photons carrying energy and momentum, then the particle side of radiation had gained a new and forceful legitimacy. But the wave side had not disappeared. The old discomfort remained, only in a sharper form. Light was not becoming simpler as evidence accumulated. It was becoming more difficult to describe in one continuous classical language. This is why the early 1920s feels so charged in retrospect. The question was no longer whether the quantum had explanatory power. The question was how far into the structure of physical reality that power was going to reach, and what older intuitions would survive the journey. That widening uncertainty is what gives this section its emotional center. Scientific communities are often imagined as moving from doubt to certainty. But in practice, they sometimes move from one kind of certainty to another kind of uncertainty. Before Planck and Einstein, the certainty had belonged to continuity. By the time of Millikan, Bohr, and Compton, that certainty had weakened. Yet no fully settled replacement had taken its place. The light quantum could no longer be shrugged off as a narrow trick of thermal radiation. It was appearing in photoelectric measurements, in the interpretation of scattering, and in the very frequency rules of atomic theory. The evidence was spreading faster than any one philosophical account could absorb it gracefully. That is why the years of confirmation remain so psychologically rich. They show a science being compelled toward transformation before it has found a stable inward language for what it is becoming. There is also a certain quiet dignity in the reluctance of this period. None of these figures was frivolous. Their hesitation was not stupidity, nor was their caution a simple failure of nerve. They were trying to preserve as much coherence as possible in a world where coherence was becoming more expensive. The wave theory had earned its prestige. classical continuity had done real explanatory work. To surrender such things lightly would not have been wisdom. What makes the history profound is that, in the end, they were not surrendered lightly. They were surrendered gradually, under pressure from phenomena that kept refusing to fit the old order without remainder. The quantum did not conquer physics through rhetoric. It conquered it by returning, again and again, wherever the old assumptions touched the world too directly. By this point, then, the crisis had passed beyond the stage where it could be quarantined. Planck's law had once seemed like a strange success inside the furnace. Einstein's photoelectric law had widened the breach into the nature of light. Millikan's experiments had made that law difficult to deny. Compton's scattering had strengthened the particle side of radiation still further. And the Nobel Committee itself, cautious as it was, had already seen that one of the most convincing confirmations of Einstein's law came through Bohr's use of it in atomic theory. That detail now becomes decisive. Once the quantum enters the atom, the old continuity of classical physics no longer merely suffers embarrassment at the edges. It begins to lose its hold on the structure of matter itself. And that is where the next stage of the story must go. By the time the quantum had begun unsettling light, the deeper problem waiting beneath it was already impossible to ignore. If radiation could no longer be described comfortably in the old continuous way, then the atom, the very unit of matter that 19th century physics had only recently begun to approach with confidence, would not remain untouched for long. The question was no longer only how energy leaves a hot cavity or how light frees an electron from metal. It was how matter itself can remain stable, structured, and capable of emitting the sharply defined spectral lines that experiment had long revealed. Once the story reaches the atom, the quantum stops looking like a local disturbance. It becomes a condition of survival for the whole physical picture. The spectral problem had been there for decades, quiet but insistent. Physicists had learned that light from rarefied gases does not spread smoothly across all wavelengths the way radiation from a hot solid does. Instead, it appears as a set of discrete lines, characteristic of the element in question. Balmer had found a simple formula for hydrogen in 1885. Rydberg and others had extended the search for regularities, and the existence of orderly spectral series had become one of the most suggestive facts in atomic physics. As the 1922 and 1925 Nobel presentation speeches later emphasized, these regularities posed two fundamental questions at once: how one element could produce many different lines, and why the lines of a given element stood in such exact mathematical relations to one another. Classical attempts to answer those questions had failed. Rutherford's nuclear model made the difficulty sharper, not easier. After the 1909 scattering experiments of Geiger and Marsden, Rutherford concluded that the atom contains a tiny, massive, positively charged nucleus with electrons moving around it. This picture was powerful, and in a broad visual sense, it felt satisfying, almost planetary. But Bohr later stressed in his Nobel lecture that once such an atomic constitution was taken seriously, the clash with classical electrodynamics became impossible to overlook. A charged electron in orbit should radiate continuously, lose energy, and fall into the nucleus. Classical theory, he said, could not even explain why spectra consist of sharp lines at all. Indeed, it was incompatible with the existence of atoms of that structure, because the electron's motions would demand a continuous radiation of energy until collapse. The old mechanics could picture the atom, but it could not keep it alive. This is why Bohr's 1913 intervention mattered so much. He did not merely refine Rutherford's atom. He changed the rules under which it was allowed to exist. In his Nobel lecture, he described the step with unusual clarity. Classical conceptions alone, he said, had made it impossible to understand the essential properties of atoms. So a new formulation was needed, one that could account both for atomic stability and for the radiation emitted from atoms. His answer came in the form of two postulates. First, among all the mechanically conceivable motions, only certain stationary states actually exist, states with a peculiar stability that classical mechanics could not explain. Second, radiation is not emitted while the atom remains in one of those stationary states. It appears only when the atom makes a complete transition from one stationary state to another, with the radiation frequency fixed by the energy difference divided by Planck's constant. The radical quality of this move can be missed now because later quantum mechanics made it familiar. But in 1913, it was an extraordinary compromise. Half conservative and half revolutionary, Bohr kept as much of the old language as he could. Inside a stationary state, the particles still obeyed classical mechanics to a considerable extent, as he explicitly put it. Yet at the moments that mattered most, the moments of stability and radiation, classical continuity was suspended. The electron was not allowed to occupy just any orbit. The atom was not allowed to radiate just because a charge was accelerating. And the frequency of emitted light no longer had to match the mechanical frequency of the electron's motion. In one stroke, the atom ceased to be fully classical, even where it still looked classical. Bohr's concrete model for hydrogen made the stakes visible. Starting from Rutherford's nucleus, he assumed that only certain orbits were permitted, that angular momentum came in discrete allowed values, and that the familiar dynamical laws still governed motion within those allowed orbits. From these assumptions, he derived discrete energy levels. Then, by applying the rule that radiation is emitted when the electron moves between levels, with frequency determined by the energy difference, he recovered the observed wavelengths of hydrogen and obtained the correct value of the Rydberg constant. Britannica's historical summary is right to call this a brilliant step forward. It was not yet modern quantum mechanics, but it showed that the sharp lines of hydrogen were not an accidental curiosity. They were the visible trace of an atom that changes by jumps. This changed the emotional center of the quantum story. Before Bohr, the quantum still looked to many people like something that had entered through radiation theory and certain awkward interactions between light and matter. With Bohr, it moved into the architecture of matter itself. The atom could not remain a miniature solar system in the old sense. It had to become something stranger, a system allowed to inhabit only particular stable states, forbidden from radiating in between, and capable of releasing light only through whole transitions. The key word here is not merely quantized, but conditional. Classical description could survive, but only within carefully bounded regions. The atom had not become incomprehensible, but it had stopped being continuously intelligible in the old way. Bohr understood that the theory was doing more than saving atomic stability. It was also giving a new interpretation to spectra themselves. In the lecture, he said that the second postulate had chiefly in view the existence of spectra with sharp lines, and that it afforded a starting point for interpreting the laws of series spectra. He then linked the spectral combination principle to transitions between stationary states, arguing that each line corresponds to the difference between two energy terms characteristic of the atom. This was a profound change in what a spectrum meant. The old hope had been that spectral lines might somehow mirror direct vibrational frequencies of charged particles moving classically in the atom. Bohr's theory said something subtler and more disruptive. A line is not the continuous song of an orbit. It is the signature of a jump. Once that reorientation happened, the atom became a place where discreteness was no longer optional. A gas could now absorb and emit only certain frequencies because the atom itself possessed only certain allowable energy states. In Bohr's lecture, the discussion of absorption follows naturally from the postulates. A spectral line emitted in a transition from a higher state to a lower one corresponds to absorption when the atom is driven back from the lower to the higher. The spectrum, in other words, is selective because the atom is selective. It does not respond continuously to every possible disturbance. It responds according to an internal ladder of allowed changes. That is a very different ontology from the classical one, even if some of its surface imagery still looks familiar. The power of the new picture was not confined to hydrogen. As the 1925 Nobel presentation speech later observed, Bohr's 1913 hypotheses did more than propose stationary states and the relation between energy levels and spectral frequencies. They also led to specific assumptions from which the spectral lines of hydrogen and the helium ion could be calculated with extraordinarily good agreement with experience. That success was large enough that, after 1913, almost a whole generation of theoretical and experimental physicists devoted itself to atomic physics and spectroscopy. This is an important shift in mood. The quantum in the atom was no longer merely a disturbing idea. It had become a productive research program, one that kept yielding contact with experiment. Still, the deepest change came not only from successful calculation, but from how the theory rewrote what could happen inside matter. Direct experimental evidence for discrete states soon reinforced the picture. Britannica notes that the existence of such states received direct support from the work of James Franck and Gustav Hertz. And Bohr himself later described their 1914 results in striking terms. Electron impacts, he said, could not impart an arbitrary amount of energy to an atom, only amounts corresponding to transfers from the normal state to other stationary states, whose existence the spectra already implied. This was exactly the sort of evidence the old continuity could not absorb gracefully. The atom was behaving as though nature had built steps where classical mechanics expected a ramp. That evidence also deepened the atom's separation from classical intuition. One of the old expectations had been that, given the right collision or disturbance, energy should be transferable in continuously variable amounts. But Franck and Hertz showed that the atom resists that picture. It does not simply soak up any offered quantity of energy. It accepts certain discrete amounts tied to its stationary states. The 1925 Nobel speech later put the matter bluntly. Bohr's hypotheses had ceased to be mere hypotheses because Franck and Hertz had experimentally proved the connection between distinct atomic states and radiation. What had once sounded like an audacious rescue of the atom was turning into a description of real atomic behavior. By this stage, then, the quantum had moved from embarrassment to necessity. The atom could no longer stay classical because every path back to a fully classical atom led into contradiction. A classically orbiting electron should radiate continuously and collapse. A classically continuous distribution of possible motions could not explain why only certain spectral lines appear. A classically continuous transfer of energy could not explain why electron impacts excite atoms only in discrete steps. Bohr's stationary states, whatever their philosophical discomfort, gave physicists something the old order could no longer provide: a stable atom that emitted sharp lines and responded to energy in quantized ways. The price was high, because it meant relinquishing continuity at the heart of matter. But By now, the price of refusing that move had become higher still. And yet the triumph was incomplete in exactly the way that matters most for the next stage of this story. Bohr's theory was fruitful, but it was also visibly hybrid. Britannica notes that it assumed electrons moved in circular orbits, and that later refinements by Sommerfeld and others tried to extend the model, only for the ad hoc mixture of classical and quantum ideas to become increasingly unsatisfactory. The 1925 Nobel presentation speech said much the same in more diplomatic language. Bohr's more specific assumptions had been outgrown. They had become too narrow for the full range of known facts. Even though the basic assumptions about stationary states and energy levels remained intact. This is the paradox that makes Bohr's atom so historically powerful. The model worked too well to discard, but too awkwardly to be final. That awkwardness is the true ending of this section. Bohr had rescued the atom, but he had not restored the old peace. He had shown that matter itself could be understood only by limiting classical description, not by extending it without restraint. The atom was now stable. Spectral lines had meaning, and the quantum had become indispensable. But the new order still lacked a fully coherent mechanics. It lived by postulates, correspondences, permitted states, and forbidden radiations. The deeper grammar had not yet arrived. The more useful Bohr's picture became, the more clearly physicists could feel its unfinished character. And so the crisis did not end when the atom stopped being classical. It simply changed form, preparing the way for a new mechanics in which the old compromises would no longer be enough. By the middle of the 1920s, the old quantum theory had become too successful to dismiss and too awkward to trust. That was its peculiar burden. It had explained enough to prove that the atom could not remain classical, yet it still relied on a patchwork of rules that did not feel like a true mechanics. Bohr's stationary states, transition frequencies, and correspondence principle had opened an extraordinary period of discovery. But even later accounts from the period make clear that something deeper was missing. In Clinton Davison's Nobel lecture, looking back on the years after 1913, he says it had once seemed as though the authentic key to spectra had finally been found, only for progress to become increasingly difficult until the feeling grew that Bohr, however deep he had dived, had not touched bottom. What was wanted, Davison says, was a new approach, a theory that would contain Bohr's virtues and go beyond them with a more genuine unifying principle. That is why this phase of the story feels so different from what came before. Earlier, the crisis had spread by discomfort. A radiation law would not fit. Light refused to behave continuously in the photoelectric effect. The atom could not stay stable without forbidden motions and privileged states. But now the difficulty was no longer only that classical physics failed. The difficulty was that the quantum replacements themselves were provisional. They worked, often brilliantly, yet still seemed to lean on a language borrowed from the world they were dismantling. Heisenberg later said that quantum mechanics arose, in its formal content, from the effort to expand Bohr's principle of correspondence into a complete mathematical scheme, and that the physically new viewpoints distinguishing it from classical physics had been prepared by difficulties in both atomic theory and the radiation theory of light. That sentence is worth holding on to, because it captures the whole transition. The next step was not another repair. It was the search for a fully new formal language. Werner Heisenberg's decisive insight in 1925 began with a kind of renunciation. In his Nobel lecture, he says that the fundamental dissimilarity between atomic spectra and the classical spectrum of an electron system imposed the need to relinquish the concept of an electron path and to forego a visual description of the atom. He even explains why the very attempt to observe an electron orbit closely enough would destroy the thing one hoped to preserve, because sufficiently short wavelength light would kick the electron off its path. In that situation, he writes, the obvious policy was to relinquish the concept of electron paths altogether, at least initially, and ask how much of it could later be carried over into quantum mechanics. This is one of the most radical moments in the history of physics, not because it is dramatic on the surface, but because it abandons one of classical thought's deepest comforts, the belief that a good theory should tell us what a particle is doing between one event and the next. What Heisenberg kept instead were not hidden orbits, but observable quantities associated with transitions. In the lecture, he says that the amplitudes and phases of the radiation emitted by the atom could be treated as a complete description of the atomic system, even though they could no longer be interpreted as arising from a definite electron path. Those quantities, linked to pairs of stationary states and to transition probabilities, formed complexes comparable to matrices in linear algebra. From there, he says, it became natural to treat the quantum analogues of classical variables as matrices and to write equations of motion for them. Born, Jordan, and Dirac then expanded this outline into a consistent and usable theory. The historical importance of matrix mechanics lies not only in its mathematical novelty, but in what it refused to promise. It no longer tried to save the picture of an electron tracing a classical orbit inside the atom. It accepted that the old visual language had reached its limit. This is the point where the documentary's central tension becomes irreversible. For a long time, physicists had been trying to preserve continuity by narrowing its domain, modifying its rules, or treating the quantum as a formal exception. Heisenberg's move made that strategy much harder to sustain. If the deepest atomic description is written not in terms of trajectories, but in terms of transitions, probabilities, and non-classical mathematical objects, then the quantum is no longer merely a strange condition imposed on an otherwise familiar mechanics. It is a different mechanics. Heisenberg's Nobel facts page summarizes the public milestone simply. In 1925, he formulated a type of quantum mechanics based on matrices. And in 1927, he proposed the uncertainty relation. But behind that simple chronology lies a change in scientific temperament. Physics had begun to choose formal adequacy over intuitive visualization. And yet Heisenberg's path was not the only one. In a sense, the other great route into the new mechanics had already been opened by Louis de Broglie. Davison's lecture recalls that by 1924, one or two promising ideas were being developed. And then appeared what he calls the brilliant idea destined to grow into present-day quantum mechanics. De Broglie's proposal that matter, like light, has a duality of aspects, possessing both wave properties and particle properties. Davison adds that the various restrictions of Bohr's theory could then be viewed as conditions for the formation of standing electron wave patterns within the atom. This was a profound conceptual reversal. The Bohr atom had looked like a classical system subject to mysterious quantum restrictions. De Broglie made it possible to imagine those restrictions as the natural consequence of wave conditions. De Broglie himself later described the step in a way that makes its philosophical elegance unmistakable in his Nobel lecture. He says that the conditions of quantum stability emerge analogously to resonance phenomena, and that it was possible to establish a correspondence between waves and corpuscles, such that classical mechanics corresponds to wave mechanics in the way geometrical optics corresponds to wave optics. He says directly that a new mechanics had to be developed, which is to classical mechanics what wave optics is to geometrical optics. That formulation matters because it changes the emotional meaning of the quantum. Instead of appearing only as a breakdown of continuity, it begins to look like a sign that the classical picture was merely an approximation, valid where wavelengths are too small to matter, and inadequate where interference, resonance, and wave structure become essential. This gave the whole crisis a new texture. Heisenberg had shown that atomic theory might have to give up its classical paths. De Broglie suggested that those lost paths could be replaced by something neither merely mathematical nor merely metaphorical, namely associated waves whose wavelengths were tied to momentum. In his lecture, he goes even further, saying that the electron can no longer be conceived as a single small granule of electricity, but must be associated with a wave, and that this wave is no myth because its wavelength can be measured and its interferences predicted. That sentence is especially powerful in the context of this documentary. It shows that by the late 1920s, the new physics was no longer content to speak only in guarded compromises. Matter itself had become dual in description. The old boundary between the wave-like behavior of radiation and the particle-like behavior of matter had begun to dissolve. The experimental confirmation of that idea made the transformation even harder to resist. Nobel's 1937 presentation speech says plainly that Davison's discovery of diffraction and interference from electron beams gave the first positive experimental evidence of the wave nature of matter, while J. Thomson's Nobel lecture remarks that the first published experiments confirming de Broglie's theory were those of Davison and Germer. In Thomson's account, thin-film electron diffraction produced ring patterns analogous to X-ray interference, with agreement good to the accuracy of the experiments and no adjustable constant. These confirmations mattered for more than one reason. They did not merely support de Broglie's thesis. They also showed that the strange dual language of the new mechanics was not confined to the hidden interior of atoms. Wave-like behavior could be demonstrated for electrons themselves on a scale visible in experimental patterns. Once matter waves entered the story, Schrödinger's contribution became both natural and transformative. De Broglie says in his lecture that the new mechanics had since been developed thanks mainly to Schrödinger. And Heisenberg likewise notes that Schrödinger and others succeeded in developing de Broglie's original concept of visualizable matter waves occurring in space and time. Schrödinger's own Nobel lecture makes clear what was so compelling about that route. Wave mechanics did not have to force the strange requirements of the old quantum theory onto the atom from outside. It let many of them arise spontaneously from an undulatory view. He says it was astounding to see how strange additional requirements developed naturally from the new wave view, whereas they had to be forced upon the old view to adapt it to the inner life of the atom and to observed facts. That is one of the deepest shifts in scientific feeling. What had once looked like arbitrary rules began to appear as consequences of a new formalism. But the new mechanics did not restore simplicity. It made the world more coherent mathematically, while also making it harder to picture in ordinary terms. Schrödinger himself says that wave mechanics confronts us with the logical opposition between an either-or of point mechanics and a both-and of wave mechanics. He admits that from the wave point of view, the infinite array of possible point paths would be merely fictitious, none enjoying the privilege of being the one really traveled. Yet he also notes that individual particle tracks are in some cases observed. He calls it confoundedly difficult to interpret these traces as nothing more than narrow bundles of equally possible paths, even though such cross-connections are necessary to understand diffraction and interference for the same particle. In other words, The new mechanics solved the atom while destabilizing the old meaning of physical description itself. Heisenberg's uncertainty relation sharpened that destabilization into principle. His Nobel facts page notes that in 1927 he proposed the uncertainty relation, setting limits on how precisely the position and velocity of a particle can be simultaneously determined. In the Nobel lecture, he places this within a wider conceptual framework, saying that the laws of quantum mechanics are basically statistical and that the uncertainty relations show how exact knowledge of one variable can exclude exact knowledge of another. He adds that classical physics seeks conclusions about objective processes by ignoring the influence of observation, whereas classical physics reaches its limit where that influence can no longer be ignored. And quantum mechanics treats atomic processes by partially foregoing their space-time description and objectification. This is not merely an epistemic inconvenience. It is a redefinition of what a fundamental theory is allowed to offer. That is why the uncertainty principle should not be thought of as an isolated aftershock. It belongs to the same movement that began when Heisenberg gave up electron orbits, when de Broglie treated matter as wave-like, and when Schrödinger found a formalism in which the old quantum restrictions emerged more naturally. All of them point in one direction. The old hope that nature, at its deepest level, would remain continuously visualizable had become impossible to maintain without distortion. Heisenberg's lecture says this in a form that is almost quiet enough to miss. Classical physics, he argues, is the limiting case of a fundamentally unvisualizable microphysics. More accurately realized, the more Planck's constant vanishes relative to the parameters of the system. That is one of the most consequential sentences in 20th century science. It means classical mechanics survives, but only as an approximation born from conditions under which the new strangeness becomes too small to notice. It is important, though, not to tell this turning point as though it produced immediate philosophical closure. The new mechanics was more powerful than the old quantum theory, but it did not dissolve every discomfort. Heisenberg speaks of complementarity through Bohr. Schrödinger remains visibly troubled by the tension between particle paths and wave description. De Broglie frames the entire recent development of theoretical physics as resting on the duality of waves and corpuscles. These are not the tones of a science that has simply become serene. They are the tones of a science that has crossed a threshold and knows it cannot go back. The progress is undeniable, but so is the loss. Physics has gained a formalism capable of describing atomic reality with extraordinary success. Yet it has done so by giving up the old assurance that reality must always be represented in the forms most natural to ordinary intuition. So this is the true point of no return in our story. Planck had found a law. Einstein had made the crisis bolder by rethinking light. Bohr had rescued the atom with a hybrid set of postulates. But here, in the mid-1920s, the quantum stops acting like a sequence of difficult exceptions and becomes the grammar of a new physics. Matrix mechanics, matter waves, wave mechanics, uncertainty, and complementarity do not merely patch holes in the classical fabric. They reveal that the fabric itself was never fundamental. From now on, the question is no longer how to save the old continuity with a few concessions. The question is what, exactly, had been trusted too deeply in the first place, and what part of that older trust was the thing that actually broke. By the time modern quantum mechanics had taken shape, it had become tempting to tell the story in a simplified way. One equation failed. A new theory replaced it, and physics moved on. But that is not really what happened. What broke was not classical physics in the crude sense. as though Newton, Maxwell, and the 19th century had suddenly been revealed as mistakes. Classical physics survived, and still survives, with immense power. What failed was something deeper and more intimate. The old confidence that the most fundamental layers of nature would remain describable in a continuous, visualizable, mechanically intuitive form. The crisis began in radiation, widened through light, entered the atom, and ended by changing the standards of what counted as an acceptable physical description. That is why the documentary's title matters. The idea that almost broke modern physics was not simply one bad law or one unlucky assumption made in one corner of thermal theory. It was the broader classical faith that energy, motion, and causation would always be representable in the smooth language that had served physics so well for centuries. In Max Born's later summary of Bohr's achievement, he says the most important assumption was that an atomic system cannot exist in all mechanically possible states, forming a continuum, but only in discrete stationary states. That is the pressure point. Continuity was not merely inconvenienced, it was denied at the level where classical thought had expected it most naturally. Planck, perhaps more clearly than anyone, understood the peculiar cost of what had happened. In his Nobel lecture, he says the quantum of action had earned full status among the universal constants, yet had still not produced a genuine quantum theory. He also says the difficulties caused by introducing it into the well-tried classical theory had increased rather than diminished over time. That is an extraordinary admission. It means the early quantum was not experienced as a clean victory of new truth over old error. It was experienced as a successful intrusion, a constant that kept proving itself indispensable while refusing to fit comfortably inside the conceptual order that had once seemed sufficient. Planck's wording becomes even more revealing when he turns to Bohr. He says that certain hypotheses used in atomic theory would once have been flatly rejected by every physicist, and that the idea of electrons in definite accelerated orbits radiating no energy, while the emitted photon's frequency does not match the electron's orbital frequency, would strike a classically trained theorist as almost intolerable for the purpose of forming a mental picture. That sentence tells us exactly what was under threat. Not merely a formula, not merely a method of calculation. What was under threat was the old alliance between mathematical success and picturability. The belief that the most basic laws of nature would also allow a reasonably continuous image of what was happening. Bohr's own work makes the same point from another direction. In his 1922 Nobel lecture, he states the postulates of stationary states with great directness. Atoms can occupy only certain allowed states. These states possess a mechanically unexplained stability. No radiation occurs while the atom remains in them, and radiation appears only in transitions between states, with frequency determined by the energy difference divided by Planck's constant. He also says this explanation differs fundamentally from ordinary electrodynamics because there is no simple relation between the atom's motion and the radiation emitted. In other words, the atom could now be saved only by giving up the classical expectation that radiation should mirror the continuous motion of charged particles in the old way. What makes Bohr historically so important is that he did not abolish the classical world outright. He suspended it selectively. In his lecture, he says the motion in stationary states still obeys classical mechanics to a considerable extent. Yet those states also possess a peculiar stability. Classical mechanics cannot explain. This is the exact shape of the break. Physics did not leap from one complete worldview to another in a single movement. Instead, the classical framework was preserved where it still worked. but denied the right to remain fundamental. It could describe approximations, limiting situations, and some internal features of allowed states. But it could no longer claim final authority over what nature is permitted to do. This is why the crisis kept deepening even after each local problem was solved. Solve blackbody radiation, and the quantum of action remains. Explain the photoelectric effect, and light itself becomes harder to imagine continuously. Rescue atomic stability, and the atom now depends on discrete states and forbidden emissions. Extend the theory further, and the old quantum rules begin to look too improvised to last. Each success removes one difficulty, but leaves behind a larger lesson. Continuity, as classical physics had trusted it, is no longer the unquestioned grammar of reality. That pattern is visible across Planck, Bohr, and Born alike, and it explains why the quantum story feels less like a march and more like a slow surrender of old privileges. Heisenberg made that surrender explicit. In his Nobel lecture, he says the fundamental dissimilarity between atomic spectra and the classical spectrum of an electron system required physicists to relinquish the concept of an electron path and to forego a visual description of the atom. He later generalizes the point even more strongly, saying that phenomena in which Planck's constant plays an important role can be understood only by largely foregoing visual description, and that classical physics seemed to be the limiting case of visualization of a fundamentally unvisualizable microphysics. This is one of the clearest statements in the whole history of the subject. The classical world did not disappear. It was demoted. It became a limiting case, valid when quantum effects are negligible, not the ultimate image in which all physical truth must finally be cast. That change is easy to underestimate because it sounds abstract, but its implications are immense. For centuries, physical understanding had been tied to the hope that if one looked hard enough, the world would submit to a picture in space and time that could be followed continuously. Quantum mechanics did not say that space and time vanish, or that causality evaporates into nonsense. What it said, more carefully and more disturbingly, was that the attempt to force atomic processes into fully classical space-time pictures runs into principled limits. Heisenberg writes that the laws of quantum mechanics are basically statistical, that only probabilities can be assigned in many cases, and that classical physics reaches its limit when the influence of observation can no longer be ignored. That is not the collapse of reason. It is the collapse of one particular classical demand on what reason is entitled to expect from nature. De Broglie's contribution shows the same break in a softer, but equally radical, form. In his Nobel lecture, he says classical mechanics is only an approximation relative to a larger wave mechanics, just as geometrical optics is only an approximation within wave optics. He adds that a new mechanics had to be developed on that basis, and that when interference and diffraction matter, it is no longer possible to assign the corpuscle a motion complying with classical dynamics. This is a profoundly elegant reformulation of the crisis. The old order is not simply rejected as false. It is reclassified as approximate, powerful on large scales and under limited conditions, but unable to govern the full reality of matter and radiation when wave structure becomes essential. That is why the deepest thing to say at the end of this documentary is not that quantum theory destroyed the classical world. It did something subtler and, in a way, more unsettling. It preserved the classical world as a surface truth, while taking away its right to be the final one. The equations of Newtonian mechanics still work magnificently, where Planck's constant is effectively negligible. Maxwell's theory still describes vast ranges of radiation phenomena with extraordinary success. Even Bohr's correspondence principle was built on the fact that classical laws must reappear in the appropriate limit. But all of this now had a new meaning. Classical success no longer proved classical fundamentality. It proved only that the world becomes classical when the deeper quantum discontinuities are too small to matter. There is also a more human answer to the question of what broke. What broke was a style of scientific comfort. Late 19th century physics had trusted that enough intelligence, enough mathematics, and enough measurement would eventually allow all phenomena to be gathered into one continuous conceptual frame. The early quantum era showed that this trust had gone too far. Planck's difficulty, Bohr's uneasy postulates, Einstein's light quanta, Heisenberg's renunciation of visual paths, and de Broglie's matter waves all point to the same lesson. Nature did not refuse lawfulness. It refused to guarantee that lawfulness would remain clothed in the forms the classical imagination preferred. And yet, that loss of comfort was not a defeat in the shallow sense. It was also a gain in honesty. Planck says the conscientious systematologist feels the gaps left behind even more sharply as research advances. That line captures something beautiful about the spirit of physics at its best. The field did not become modern because it found a theory that made the world easier to picture. It became modern because it accepted, reluctantly and piece by piece, that the world was not obliged to preserve the old union between intuition and truth. The quantum of action was granted full citizenship not because it soothed anyone, but because facts forced that acknowledgement. In this sense, modern physics was not shattered by uncertainty. It was matured by submission to evidence that refused the old peace. This is also why the history never becomes merely technical. However dense the mathematics may later grow, at bottom, it is a story about what science is willing to give up in order to remain faithful to reality. It gave up the continuity of mechanically possible states in the atom. It gave up the hope that radiation could always be understood in one classical image. It gave up exact trajectories as the unquestioned core of microscopic explanation. It gave up the assumption that prediction must always take the form of a complete account of what objectively happens in space and time, independent of how it is observed. None of those concessions came easily, and none was made all at once. But together, they mark the real breaking point between the 19th century expectation of nature and the 20th century recognition of its deeper strangeness. So when we ask, at the end, what almost broke modern physics, the answer is not the ultraviolet catastrophe by itself, or Planck's constant by itself, or the photoelectric effect, or Bohr's atom, or uncertainty. Taken one by one, those were the places where the fracture became visible. What actually broke was the classical promise that reality at its foundations must remain continuous, fully visualizable, and mechanically intuitive. What emerged in its place was not chaos, but a different kind of order, lawful, exacting, experimentally fertile, yet statistical in part, discontinuous at crucial points, and only partially representable in the images the human mind had once trusted most. Heisenberg's formulation may be the clearest final summary. Classical physics became the limiting case of a deeper microphysics whose full content cannot be visualized in the old way. That was the loss. But it was also the opening, because once physics accepted that loss, it gained the modern world. By the end of this story, what seems to have broken is larger than any single law of radiation, any single experiment, or any single scientific reputation. What gave way was a certain kind of confidence, not confidence in reason itself, but but confidence that reason would always find the world arranged in forms that matched its old intuitions. For a long time, physics had trusted that nature, however subtle, would remain continuous, visualizable, and obedient to the habits of classical thought. But when heat and light refused to fit, that trust began to loosen. And from that loosening came a new century of science. There is something quietly humbling in that. The path into modern physics was not a clean march from ignorance to knowledge. It was slower than that, and more human. The very people who opened the new world often resisted it. Some verified conclusions they did not like. Some used ideas they were not yet ready to accept. Some stood with one foot in the old language and one in the new. And perhaps that is why this history still feels so alive. It reminds us that discovery is not always the moment when certainty arrives. Sometimes it is the moment when certainty becomes impossible to preserve. So when we look back on this turning point, we are not only looking at the birth of quantum theory, we are looking at one of those rare moments when science was forced to become more honest than it was comfortable being. A small problem in a furnace became a doorway into a stranger universe. And the cost of passing through it was the loss of an old intellectual peace. Yet there is also beauty in that loss. Because the deeper lesson of curiosity is not that the world must fit the shapes we prefer. It is that reality, when followed patiently enough, can lead us beyond them